All right, welcome back to another stream on the creation of this ESP32 e-paper development kit. Last time, if you remember, I went through sort of the reasoning behind the board layout the way it was. I haven't changed anything. We're still going to do that. That's going to be in the very next stream. What we're going to do in this stream is we're going to create a footprint for this e-paper display connector over here. I just chose one that came with KiCad, and so it's this J5 right here. If you look at the screen, this J5, this is not the correct footprint for the e-paper connector that I use on my existing hardware, and the one that I use on my existing hardware works really well, so I'd like to use it again. Sometimes they're close enough and the footprint will work. In this case, it won't. These MP pads out here that are used to really secure the connector to the circuit board are too far ahead. Like the feet on my actual connectors are like back in here, and so they wouldn't even, the only thing, if I use this footprint, the only thing holding the connector to the printed circuit board would be the actual pins, which is just asking for trouble. It'll tear right off as you're trying to connect it and disconnect it. And so we're going to create a footprint. For those that were here last time, I had ordered a pre-pilot. I called it the pre-pilot run to check the board layout. That's this yellow line, and I found that the footprints, not the footprints, these little notches for the standoffs in the case were slightly off. I did decide to correct these ones on the left, the top and the bottom over here. I adjusted those. They were at the right position, so the center point was right, but these back ones here, like right here, was off just a bit. Like it was just a little bit too tight. It did fit and you could force it, but zero tolerance. So if somebody 3D printed a case and it was slightly off, there was just no way that it was going to fit. And so I widened that a little bit. And so that's the only change that I've made to this since the last time you saw it during the last stream, is I changed the size of that and the size of this down here. So all that's good. Now, as far as footprints, I did verify that this USB footprint over here for the connector, this one I did just choose out of the KiCad library. It turns out that the USB connector that I've used before in previous production runs fits just fine in that. So we're going to leave that. So at this point, all of the footprints look good with the exception of two, and that's the connector that we're going to do today, and then the switches. We'll look at, we'll do this one. I looked at this switch on the Osh Park board, and it's, I don't know, I don't like it. I think I'm going to look at different, these aren't actually switches, they're labeled SW1, they're buttons. They're going to be buttons on the board. I don't think I like these footprints, so I'm going to probably change those as well. I won't do an episode or stream on those because it's very simple. It's just two copper pads, and just the size of them and the width, the spacing between them is all that matters. It's very simple, not very interesting to see. So when you're doing board layout, so again, the whole point of this is that we're creating a dev kit from scratch. We've created the board layout, and I've done this specific crazy yellow outline that you see here because I have an injection molded case that this will fit into nicely. I also have the parts files, the STL files that I can publish for people to 3D print them. So if they buy the dev kit with this shaped board, they can print a case, or I could sell them. Either way, it doesn't really matter. It has a case already that fits perfectly that you can mount the screen into, and you don't have to worry about that. So it's kind of a nice little feature. And that's why the board is kind of a funky layout like you see it here. And so what you have to do is you create your board layout. It could be like this. It could be something that's long and skinny so that it would fit on a breadboard, or it could be, you know, anything you want. You can define whatever board layout you want. You define that layout with this, again, this yellow line. Then you have to place all the components somewhere, but before you really can place all of the components, you need the correct footprint for all of those components. And the footprint, again, is this sort of the way these pads are laid out. Like capacitor C11's footprint is just these two pads. That's the copper that's going to lay down in fab for you to solder your components to. And so you need the correct footprint for everything so that you can lay everything out correctly. For example, this J5 over here that we're going to mess with today is bigger than the actual footprint that we're going to end up building. And so if I placed and positioned everything around this improper footprint and then decided to change it later, I'm messing everything up. So you want to make sure that all of the footprints are correct before you do final placement of all the parts. And once that's done, then you can place all the components, and then once all the components are placed, then you can route the board. This is a process, and that's why I want to show it. And so what we're going to do today again is we're going to create a footprint for J5. This is not something that I am an expert at, and so don't expect this to be a smooth walkthrough how-to. I'm going to fumble through this. I've tried it once briefly so I wasn't completely flying blind during the stream here, but we're going to do that. So we're going to do that footprint today. I'll make a decision on the switches. Those are trivial, again, like I said. And then next time we'll be doing actual component rearranging, moving things like I had talked about in the last stream. And so one more piece of background information here. Let's see. Let's open the schematic view. So you've got your schematic, and I've already done the walkthrough of this, but here's the display portion of the schematic, and you have this schematic symbol for the connector. And it's very simple. It's just 24 lines because it's a 24-pin connector. And so you can do the schematic without the footprint, but then back over on the PCB, we need to assign a footprint to match it. And so right now that's this, like I said, this J5 here that was just built into KiCad. And what's hard about creating footprints like this, unlike switches that are just very simple pads, is that you have to get this information. Most data sheets will have this. It's really hard if the data sheet doesn't have this information because, let me switch camera. It's really hard when the data sheet doesn't have this, because then you have to get calipers out and like measure things and figure out like what the pitch is and the pin width and length and stuff is. But most data sheets will have this information for parts like this, like connectors and other, I don't want to say non-standard, but outside of your very passive components like capacitors, resistors, inductors, transistors, etc. The data sheet will have a recommended footprint. They call it a land pattern. And after some digging, there's the part that I'm using for the e-paper connector is no exception. It has the data sheet, but it is, I'm going to pull it over onto the screen. So I'm going to show it to you on the screen, but first I printed out, because as I will show you here in a minute, and I don't know if you're going to be able to see this. I'm going to try and put my finger right in front of it. All right. That is the footprint for the parts that secure it to the PCB. And if you can see, there's kind of a bold line, and it says pattern, what does it say? Pattern for mounting plate fixing. And I'm going to switch back over to my camera here. Let me pull the data sheet over here. Now that I know it's bolded, it's easier to see, but look at all of these lines going everywhere. Like, everything's got a dimension, and the pins are easy. They're a 0.5 millimeter pitch. Pitch meaning that's how far they're spaced apart center to center, and you can see that right here. Right here is 0.5 millimeters, and then it gives you the tolerance, plus or minus 0.03 millimeters. But this is kind of a weird shaped pattern for the mounting plate, and we're going to decide here, and I'll show you this in a minute. We could make it this shape, but it's kind of hard to see what is the actual land pattern, what's the actual fix, mounting plate, which is this little fork looking thing. That's not part of the land pattern. We're not going to do that in copper. Excuse me. And then everything's got a dimension on it. But what's really interesting about this is it says pattern for mounting fixing plate, and it's this design over here. I'm going to kind of trace it with my mouse. Whoa. And then another one here on this side. The problem is you've got so many lines going which way, it's hard to tell like which one is part of the land pattern and which one is just a line that's telling you what the dimensions are. And I found that that's easier when you print it out. And I've actually written down a bunch of dimensions here, because what is also fun about this is they don't give you every dimension that you need. They give you enough dimensions so that you can solve for the dimensions that they don't give you. And that's what makes this, you know, a hassle sometimes, especially when you're dealing with something like this footprint there. Sorry, this land pattern here has 1, 2, 3, 4, 5, 6, 7, 8 sides to it. So you have to calculate 8 different lengths if you want to create this exact land pattern. And they only give you a portion of those, but you can solve for the ones that they don't give you, which I get why they do. There's only so much space and it's already really noisy, as you can see here, but that's annoying. Like, for example, let me show you one of these. 0.5 millimeters is the distance. Can I zoom on this more? Yeah, let's make this nice and big so you can see it. Okay, this distance, oh yeah, see, it's not even this distance. It's this distance right here. From this point to this point is 0.5 millimeters. Now, the other part of this is from here to here, which is 1.1. So you've got that, and then 2.3 gives you this. Oh my goodness, are they going to tell me which one of these did they not give you? 1.4. Ah, there we go. Okay, here's one. This one right here, from this point where I have my mouse to this point right here, is not given as a dimension. However, you're given the dimension from here to here, which is 2.65, and you're given the dimension from right here to right here, which is 1.4, which means you can calculate this length right here. I wrote all these down because I didn't want to have to calculate them for you on stream. 1.25 millimeters. And so it's stuff like that where, why can't we just tell you that this is 1.25 millimeters? The same thing happens on some of these other edges. And so I find it's helpful to print them out because they get, again, it's easier when I just have all the numbers written. And so let's create a footprint here. So what we're going to do is we're going to highlight this part. We're going to press E for edit. And we're going to do, I think we want to do change footprint, not edit footprint, because we don't want to edit the existing footprint. Change the, well, maybe not. Okay, I take that back. Let's do, oh, sorry. Edit. We'll do edit footprint. And from here, we're going to do, there's up here in the corner, new footprint using footprint wizard. And this is something that's really nice about KiCad. It's got this footprint generators for some very simple components. And you think, oh, it's not here, except you scroll down and right here we have the FPC connector, which is what this connector is. FPC stands for flat printed cable. Another term you'll hear is FFC, which is flat flexible cable connector. So anyway, this is what we're trying to do. It's an FPC or an FFC. So we're going to select that, hit OK. And you'll see it creates a brand new footprint with some default values. Now, the N parameter here is the number of pins. Excuse me, in our case, that's going to be 24 pins. And this is really cool. The way you used to have to do this, like back in the day when I used Eagle and some other things, you would have to like draw each of these pads, give them a number, space them correctly, make them the correct width and height, and set the pitch and stuff and figure that all out. This is really nice that KiCad has this footprint generator. So we've got our 24 pins. We don't have to mess with that at all anymore. The pitch is 0.5 millimeters. Now the width, I'm going to pull this back over. It defaults to 0.25 and the height to 1.6. Again, this is in the data sheet. So the width is listed right here. 0.3 is what the width is, not 0.25. And then the height from here down to here, you can see is this value over here. It's 1.4. And so we're going to change that to 0.3 and 1.4. Let me drag this back over. So the width is going to be 0.3. and the height is going to be 1.4. And then it makes these adjustments for you on the fly. And so that's great. Now out here, we still have, excuse me, getting over a cold. We still have these, again, for the mounting plates, these pin 0. And that's going to be, if I'm going to open this up a little bit. We've got pads and we've also got shield. So I'm going to select shield. And now this gets a little interesting. The way I found to best play with this, if you're not sure what they mean, is just remember the number and try 0 to see where it's going to center off to see what the offset looks like. So the shield to pad is going to be the distance from this to the pad. Now you might think, oh, if I set it to 0, it'll be right up against the pad. But as you'll see here, I'm going to set it to 0. That makes it overlap. So it's the 0 point that it's using is the center, and it zeroes it to the center of this pad. And so shield to pad, we don't want to be 0, but it helps you to understand, again, what this value is. And so if we change it back to 1.6, it puts it back out there. And now I don't remember what the distance is on this from the shield to the pad. So it's 3.1. Okay, so let's look at this. From the center of the first pad, it's 3.1 millimeters to the edge of this. And so let's come back to the shield to pad and from top. Let's just set the width and the height to start. So again, from the wizard, we can't create a weird shape on this pad that we need. We can do that after we use the wizard to give us a starting point. The wizard's used to give us a starting point, and then we can adjust it after that, which I'm not entirely sure how to do, but we'll look at it. And so the overall width, what we can do, I'm going to bring this back over, is instead of notching it like this, we'll just make one big square that's the height and the total width. And we can alter it later. So the total width is 2.65. So let's change the width to 2.65. It's going to make it nice and wide there. And then the height, I won't bring it back over. I'll just tell you what it is. It's 2.3 millimeters. So 2.3. So that's the big outline of the pad, and we'll worry about making it more, the correct shape later. And now the from top, let's see this one. If we set this to 0, it's currently 1.3. This is the offset top to bottom. So that's going to shift it up. 0 puts it perfectly in line with the pins. We don't want that. And so let's set it back to 1.3. What we want to do is move it down to what looks like about the center of the pins. And so since the pins are 1.4, we're going to do that, and it looks like, yeah, but see, that's not right. That's below the center of the pin. So the center line is right here. So what we really need to do is, again, let's see, set it to 0. That's centered. We want to move it down. We want to move the midpoint of this. Sorry, we want to move the top of this down to the midpoint of these. And so I guess that would just be half of the height. 2.3. I always need to, let's see, 2.3 divided by 2, 1.15. So I think 1.15 is what would center it that way. 1.15. Yeah, so that looks right. So the top of the pad is right in the middle of the pins, and if we pull this over, the top of the pad here looks to be about right in the middle of the pins. So I think that looks good. Okay, so that looks good. Let's push it back out a little bit. A lot of this is trial and error, and what you can do on these, and I'll show you this, probably not today. I'll mess with it after we've done the stream here. But what you can do is you can print this out at a 1-to-1 ratio on just a piece of paper and then get the actual part. And so instead of having to actually pay for fab and do another run like that, you just print it out on regular paper and then lay the component down on there and see if the pins line up and the footprint looks right. That's a great way to save yourself money and time of actually doing a run. You don't actually have to produce a printed circuit board with the footprint to test the footprint. You can just print it out. So, okay, so I think we've got the from top down. Now we just need the shield to pad. And okay, so the shield to pad says the left edge of this footprint, the farthest edge of the footprint after we modify it, needs to be 3.1 millimeters from the center of this pad. And so if I do shield to pad and set it to 0, that's going to center it on that pin. Yep, okay, it centers it on that pin. And now I want this far edge to be 3.1 millimeters. So right now, this edge is half the width from the center. So let's bring the calculator back up here. Just a lot of basic math in here and adding. So the width that we said was 2.65. 2.65. If we divide that by 2, divided by 2, that means this edge is 1.325 millimeters from the center of this pad, but it needs to be 3.1 millimeters. So I think if I just do 3.1 minus that, no, not 31, 3.1. Oh, it's not gonna let me do that. Okay, whatever. It's giving me a hard time, calculator. 3.1 minus 1.325. 1.775. So if I do shield to pad as 1.775, that should be right. Okay. And then you can just eyeball it. So like you can see this, I can't remember what they call the pink. The actual copper is the solid red. You can see the space here is a little bit smaller than it is here. And just as an eye test, let's blow this up. The space in between these pads does look slightly smaller than the space there. So that the sanity test passes that we have actually got the basic dimensions of this right. And so now that we've got that, we've got the pads, we've got 24 of them, we've got these bigger pads at the correct spacing, I think we're all set. I don't know. Okay, here we go. Export footprint to editor. There we go. So now I have it in the editor, the footprint editor, and it's unsaved. You can see it says it up here. I think right now, let's save this. Save changes to board. I don't want to do that yet. I want to do save. Okay, and we're going to call this the, what? This is the Amphenol. Oh goodness, let me get my parts bag. It's not this one. We'll call it the Amphenol SF. I'm just grabbing this right off the bag from DigiKey. SVR. Can I do dashes? Yeah, there we go. 3STB. We'll just call it 3STB. So SFV24R 3STB. And then save in library. I created a custom library called StatFeeder. So I want to save this in my StatFeeder library, which is just a part of the local project here. In fact, let me show you that. I think that would be helpful to see. Oh, here we go. Hardware. Okay. Okay, I have this stat feeder hardware, EDA, and then the library here has this SOD 923. And now I'll go ahead and save this new footprint into the stat feeder library. I'll hit save. And then now in that lib folder, I have a new .KiCad_mod file. And so this library is local to the project here, which, by the way, get back to it. I'm saving everything with this project. I'm really enjoying saving this all in a GitHub repo. It's all version control. So like when I get to a good point where I feel like I've got something accomplished, I commit the files. I'm even doing a diff on the actual KiCad files to understand what changes inside of them. And then that's been super helpful, because then if you get to a point where you make a mistake or you screw something up and you're like, oh, I wish I could go back to where it was, you just use Git, the features of Git, to do that. You just revert a commit, go back a couple of commits, and you can go back to where you were. And so I find that it's very helpful to keep all this stuff in a GitHub repository. So, all right, so this is the basic footprint of our connector. Now, you'll notice what it doesn't have is, let me see if I can show you. I'm not sure if this is going to work. I'm going to switch to the cam again to see how it works. Oh, focus. Okay, there we go. Right there at the top middle, that's the connector with the kind of funky shaped landing pads for the mounting plate. But you can see that white line is an outline of the actual connector. So like it goes out and it shows the actual, let me bring this back over and show it to you again. So this is the landing pattern, but if we scroll up in the sheet here, it'll show you the outline. The connector has this sort of L shape off the side. That's the actual plastic connector. Oh, you can't see. What am I showing to you? Right camera. Right here, sorry. It has this L shape right here. And so the silkscreen on my existing layout covers that. This is just a square. The silkscreen is white on the board when you get it from the fab house, but in this case, the green or teal or whatever color you want to call this, this is what's going to be the actual silkscreen that's going to print on the printed circuit board. And so we could just leave it like this, but it's always better if you can have the silkscreen come out the actual shape of the part, and that helps for when you're back over here in layout. It helps you know, like in this case, the part's going to come way out to here. So even though there's only pins right here and right here, I can't go and you know, I can't put R16 right here because it's going to be underneath the actual connector. And so it's helpful to have the silkscreen, not just because it shows you how the parts will lay out on the board, you know, when it's printed, but it helps you during layout to know where to not place other components. And so, and I don't know that I need to stream that. Like, I don't know that I need to show you. What I'll basically do at this point is I'm going to look at this drawing, figure out some of these dimensions of the physical thing. I'm not going to be looking at the land pattern now. Like, again, the land pattern does show like, oh, this is where you should draw the silkscreen, but there's no dimensions of how this, the land pattern doesn't give you dimensions of what this line should look like other than this big long width here, but it doesn't tell you how far it needs to come out here and down. None of those dimensions are given. And so what I'll do is I'll come up here to the actual mechanical drawing, and here they are. So like from the top of the connector here, it's going to be 4.2 millimeters down to the front of the physical connector. And so I'll come back, like I said, I won't do that here on the stream. I'll come back and draw the silkscreen layer out for that so that we have a better idea for when we place it back on the board. Now, I'm going to wrap up the stream. Actually, I'm not even going to stream how I'm going to do this footprint adjustment because I'm not really sure how I'm going to do it, to be honest. But right now it is placed where it would actually work to solder the component onto the breadboard. So I could leave it just like this because it's bigger, it's all encompassing of the actual LAN pattern that the data sheet says that we should use. So I could leave it like this. Now, why? Again, let's come back to here. If you see there, focus for me. You know, again, it's that weird shape. Let me see if I can point to it. Right there. Oh, right there. It's that weird shape. Why would we pare this down to be that kind of very specific odd shape? And the reason that you would do that is because the more copper that you have on the printed circuit board, the more solder paste it's going to put down. So when the fab house goes to do, or the assembly house goes to assemble this, and you've got this pick and place machine, they're going to put a whole bunch of what's called solder paste on all of the copper pads, and then they're going to place all of the components on the circuit board, and then they're going to put it in what's called a reflow oven. It's going to heat it up using like this reflow profile where it's going to go through certain temperatures, hold for a certain amount of time. All that solder paste is going to reflow and essentially solder every component to the board at the same time. These aren't being hand soldered one at a time by somebody. This is all being done by machines. And when you have the pad like this, they're going to put solder paste on the whole thing. It's going to take longer to heat that amount of solder paste up. And so you could run into a couple of things. One is if I make this pad just too big, it's not going to solder correctly based on the solder reflow profile of the component. And if we come back to this right here, I can't highlight it, so it's just right here above me, right here above the window. It says the housing will withstand exposure to 260-degree peak temperature for 10 seconds in a reflow soldering oven. And so you've got 10 seconds at that temperature before the plastic starts to just melt and the part gets ruined. And so if you put too much solder paste and you make this pad too big, it might not reflow properly and seal or solder correctly to the board. And so you're going to have a weak joint and it's not going to be held on there correctly. Or if you want it to solder correctly, you're going to have to leave it at that temperature for too long so that it will solder the pad correctly, but the part's going to melt. And so there's a lot of these things that you got to figure out and be aware of as you're putting these boards together and figuring out how to create these pads. And so it's best to do the recommended LAN pattern because they've probably done some actual math around the surface area of that, the reflow, and the time that it needs to reflow. The other thing is just it's going to use extra solder paste. And so you want to, would we be okay leaving it like this? Maybe. I'm going to go with maybe. I guess I don't want to find out. Like, I'm just going to spend the time to now come in here and I can actually create raw copper. At this point, you're in the editor. You can like grab, I'll just show you this tool real quick. Like I can draw, you know, let's say I want the pad to look like that. Okay. So now it's on the silkscreen layer. I just right click on that. Or sorry, I don't right click on it. I edit it. I change the layer to front copper. And ta-da, I've got a pad. Like that's a new pad. So what I'm going to do now, and I won't stream this, is I'm going to come and I'm going to actually use these tools over here to create the exact shape that this is supposed to be, make it copper, the copper layer. And then I will copy it, come over here, paste it over here, and then that should do it. The other part I told you, we're going to do the silk screen to do the proper layout and dimensions of the actual connector. And then after that, I figure that's probably another, I'm going to say hours worth of work to do. Then we will have the footprint that we need for our e-paper display connector. And so you can see the amount of work that goes into creating these things. is a lot. And again, I'm not a pro. A pro could probably do this, in 10 minutes. But that's why I want to show the journey. Like this is all the stuff that goes into building the dev kit that we're trying to build. So that's it. That's going to do it for today. Like I said, I'll finish these things up, and then on the next stream, I'll show you how it turned out. I'll tell you about any problems I ran into doing that. And we'll move on with layout, moving all those parts around so that we can begin to do trace routing in a future stream as well. And so that's going to do it for this time. Thanks so much for joining the stream. I always forget to check to make sure, see if anybody dropped in live to chat. Sorry about that if I missed you. So we'll see you next time. Okay, YouTube. That's it. I just ended the stream. These videos are long. And again, I want to show the raw process. And so I hope that you're finding value in that. But for me to know that, it would be really helpful, and it would mean a lot if you could take a minute to leave a comment. If you've made it this far, first of all, I love you. Thank you for staying. I would love to hear some feedback, what you want to see more of. Are there parts of this process that I'm not showing you that you have questions about? Let me know so that I can tailor the content in the streams. Right now, I'm just sort of going through the process and showing the process. Let me switch the camera here. I'm just showing the process, but if there's things that you want to see more of or things you want to see less of, let me know, and I'll tailor the streams to that. I want this to be as valuable as possible. I'm going to be doing this work anyway to create the dev kit. I want to share the things that are of most interest to those of you that are actually watching, so that if you want to do something like this, you have an idea of what's involved, and I'd be happy to try and answer any questions that you have. So thanks so much for watching. Really appreciate it. And join us next time. Again, we're going to be doing more board layout on the ESP32 ePaper dev kit. So thanks, and have an amazing day.